Okay, well, we still want to go over these quiz problems because these are good problems. The more that you do, the better that you'll get. And of course, the better that you get, who knows what doors will open in the future. And these are still good to practice because, you know, we still have an exam coming up, still have homework, and the more we know, the better that we'll do. Number 1, given that A0 is 137 and A sub n is n minus 18 times A sub n minus 1 plus 3, find A sub 20. Okay, well, that's going to take us a while. Well, let's start. We know A0 equals 137. A1, what is that? Well, that would be 1 minus 18, because, right, n equals 1. 1 minus 18 times the previous number, which is 137 plus 3. So that's what? Negative 17 times 137 plus 3. That's a number. Equals something, right? All right. A2. Well, that would be 2 minus 18 times A1 plus 3, which is, well, 2 minus 18, negative 16 times the previous number, negative 17 times 137 plus 3 equals, Okay, this is not looking very promising right now, right? These are huge numbers. We haven't even tried to simplify because they're terrible. They're terrible looking. How are we supposed to get up to 20? I mean, by the time we get to 20, we'd just be like filling up the whole page. Let's think about this for a second, though. I mean, they asked us to find it, so there must be something going on here. Now, notice, this is sort of like the interesting part, right? If it wasn't there, it just says, you know, A sub n would be the previous term plus 3. But it is there. And let's think about what this is doing. See, the first time, you multiply by negative 17. The next time, negative 16. How about the next time? Negative 15. All right. Is there a really good time? Now, you might be thinking, okay, well, what do you mean by a really good time? Now, remember, there's a very good rule that we always have in the back of our mind. So what's our good rule? Our good rule says 0 is a friend. In other words, we oftentimes think to ourselves, do I have a way to incorporate 0 into my problem to make things easier? Well, let's look at this. This n minus 18, it varies with n. What's a really good choice for n? Like something that will make life beautiful. Well, I think you can see it. If 0 is a friend, if I could make that 0, well, what does it? The answer is n equals 18. So I could imagine I could have gone to A17 equals some big number, which I don't know what it is, so I'll write down some big number. And then A18, according to the rule, would be 18 minus 18 times A17 plus 3. But wait, 18 minus 18 is 0. If I multiply 0 times some big number, doesn't matter how big that number is, you're not going to recover. So what happens? The first term goes away. Even though I don't know what A17 is, it doesn't matter. A18 is 3. Nice. Okay, but that's what we don't want A18, we want A20. So how about A19? Well, according to the rule, so that's when n equals 19. So 19 minus 18 times the previous number plus 3. Well, that's 1 minus 18, which is 1, times the previous number. Previous number is 3 plus 3 equals 6. Okay, these are numbers I can work with. How about A20? Well, that would be 20 minus 18 times the previous number. And then I add 3, right? 20 minus 18, previous number, add 3. So that's 20 minus 18 is 2. Previous number, 6, plus 3 is plus 3. That's 12 plus 3 equals 15. Ah, nice. So that turned out to be a lot easier than it was looking at the beginning. Why? Because we used our rule. 0 is a friend. And we should use 0 as much as we can. 1 is also a good friend, but I would say 1 is probably not as good as 0. 0 is just amazing. All right, number 2. Suppose we have that a0 equals 1, and if I want to find a next number, I take the square root of 1 and the previous number. Now, it's a sequence which converges. And we're just told that. We don't have to prove it, we're just told that. Determine the limit of the sequence. Now, you might say, well, do we start writing down numbers? So, for example, a0 is 1. a1, that's the square root of 1 plus a0, right? 1 plus 1. What's a2? That's the square root of 1 plus the previous term, square root of 1 plus 1. How about a3? That's the square root of 1 plus the square root of 1 plus the square root of 1 plus 1, right? Square root of 1 plus the previous number. And I'm not sure what these numbers are doing. I mean, this one, that's not so bad. That's square root of 2. So we're told, of course, this is converging to something. And what does it look like? The square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of 1 plus... keeps going. Now, we're not going to try to figure it out by looking at these numbers. For one thing, these are just a couple of numbers. We're already having a hard time sort of getting a good handle on it. We're not going to get infinitely many. But for another, it's not a very efficient way to do it. So let's think about it. We know it converges. So that says the limit as n goes to infinity of a sub n equals something. We'll call it L. L for limit. So we know it converges, it equals something. We'll call that something L. Now, what do we have? Well, let's think about the two sides. So a sub n, which is the square root of 1 plus a sub n minus 1. Now, let's let n get big. As n gets big, what does a sub n do? Well, we know what happens. As n gets big, a sub n goes to L. So this side goes to L. But that's going to equal to what happens over here when n gets big. Well, the square root and the 1 and the plus, okay, that's just, it is what it is. What happens to that? A sub n minus 1. Now, we know that a sub n is getting close to L. What is a sub n minus 1 getting close to? Well, it turns out the answer is, it's L. Now you might say, what? Why? Well, because remember, we have this list. A0, A1, A2, and there's like AN. And that's number close to L. Now where is AN minus 1? It's right next to it, right? They're right next door to each other. So if this is close to L, this is close to L, because everything's getting close to L at the end. So whatever our limit is has to satisfy that relationship. Well, that's not so bad. Let's solve for L. So let's get rid of that square root. L squared equals 1 plus L. Now what happens? Well, let's move everything across. L squared minus L minus 1 equals 0. That's a quadratic. Does it factor? No. But that's okay. We can still solve for it. Quadratic formula. L equals negative b, 1, plus or minus the square root, b squared, 1, minus 4ac. So plus 4 all over 2. So it looks like we have two possibilities. Now, we know we can't have two possibilities because it's only going to converge to one thing. That's how limits work. They can't go to two different things. So which one of these is the right answer and which one of these is an imposter? Shouldn't belong. Well, let's think about it. We know that we're looking for something where if we look at these numbers, you get a positive number 1, square root of 2. And this is something big. In fact, all these numbers are going to be at least as big as 1. Look at this minus 1. How is root 5 compared to 1? The answer is root 5 is bigger than 1. This number is negative. So that can't happen. So, by process of elimination, That's our answer. So what we have is that a sub n converges to 1 plus the square root of 5 over 2. All right, good. Now, that's the answer. But let's pause for a second. 1 plus the square root of 5 over 2 is not just any number. In fact, it's a beautiful number. Have you ever heard of this number before or seen it somewhere? It has a name. It's called phi. Or, depending upon how you pronounce things, phi. What is that? It's the golden ratio. Now, what is the golden ratio? Well, the Greeks, they had this belief. They said, you know, that there's a rectangle that would be the most beautiful rectangle. And the most beautiful rectangle would be something that looks roughly like this, where if this side is 1, then this side is phi. Now, what makes this rectangle so beautiful? Well, what makes this rectangle beautiful is if you cut off a square, then this smaller rectangle left over is proportionate the same as the original rectangle. And they thought that would make the most beautiful rectangle. And so that was their belief. Were they right? Probably not. In fact, there was people who one day they printed out a whole bunch of rectangles of different sizes, and they went out, people, and they held out this sheet of rectangles and said, point to the rectangle which is the most beautiful. They did not pick that one. So the Greeks were wrong about the golden ratio. Well, what can you do? You know, still, it's a nice idea. All right, well, number 2. Next one. Ooh, now we're doing sums. Find a sum, n equals 2 to infinity, 6, divided by 4n squared minus 9. Now, there's a couple of things to note. First off, there's this word find. So when you see the word find, that means we want to find the value for it. And when we want to find the value of a sum, at this stage, there's only 2 things we can be looking for. Namely, we can either be looking for something which is geometric, because that's something we can find the value for, or something which is telescoping. Now, the question is, which tool do we need here? Well, if I'm looking for something geometric, I want to have something to the n. I really want an exponent upstairs with n. So, I check, do I have that? The answer is no. So, it's not geometric, so we need to be looking for telescoping. So, what does it mean to be telescoping? Well, what I really want to do is find a way to write this in a different way. Namely, I want to write this as something minus something, where these two somethings, and I know that's a very non-technical term, but I want these two somethings to look very similar, just sort of slightly shifted from one another. So that's what we're after. That's our goal. So let's think about this. How can we get from something that looks like this to something that looks like that? Well, what do? Well, not surprising, we say, what if this were an integration problem? What would we do? So 6 over like 4x squared minus 9. Well, if it was an integration problem, what we would do is we would do partial fractions. But because it's a summation problem, what we're going to do is partial fractions. See? Still works, right? So if you think of 6 over 4n squared minus 9, you can factor that, because this is really 2n quantities squared minus 3 quantities squared. So that's 6 over 2n minus 3, 2n plus 3. So that's something over 2n minus 3 plus something else over 2n plus 3. Clear the denominator. 6 is going to be equal to a times, now when I multiply here, the 2n minus 3's will cancel, so I'll be left with the 2n plus 3, then plus b, and on this term the 2n plus 3's cancel, so I'll be left with the 2n minus 3. Now, we must choose. Well, you don't have to, there's more than one way to do it, but I like to do the choose way. So let's choose some nice values. Suppose we choose n equals 3/2. Well, why that value? Well, 2 times 3/2 is 3. Subtract 3 is 0. And remember, 0 is a friend. So, if we choose that, we get 6 equals a. And here we'll get 3 plus 3, which is 6. And that term drops out. Which tells us a equals 1. Now, what's the other choice? Well, to knock out this term, choose negative 3/2. And what does that get us? Well, 6. This term will become 0 times a, which goes away. And then we'll get negative 3/2 times 2, which is negative 3 minus 3 is negative 6. So b times minus 6, which tells us that b has to be negative 1. So this looks like 1 over 2n minus 3 minus 1 over 2n plus 3. See, that's what we want. So our sum has become that. Good, good, good. Okay, what happens next? Well, the next thing is for us to do the following. And what I like to do is I like to say, okay, what's happening here? Well, what's the first term? N equals 1. So you get 1, divide that by 2 minus 3, which is minus 1, minus 1 over 2 plus 3, which is 1/5. So minus 1 minus 1/5. Oh, wait a second. I don't start at 1, I start at 2. Ha 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 ha. Mwah ha ha ha. Okay. Pay attention to your index. Okay, when n equals 2, what do you get? You get 1 over 4 minus 3, that's 1, minus 1 over 4 plus 3, which is 1/7. Okay, that's the first term, 1 minus 1/7. All right, yeah, all right, what's the next term? Plus, so this is n equals 2. Next term, n equals 3. So 6 minus 3, that's 1 over 3. And here, it'll be 6 plus 3, so minus 1 over 9. Plus, next term, that'd be n equals 4. So that'd be 1 over 8 minus 3, 1 over 5. And 1 over 8 plus 3, which is 1 over 11. And then the next term will be n equals 5. Well, what's that? 1 over 10 minus 3 is 1 over 7. And then 1 over 10 plus 3 is 1 over 13. And, oh my gosh, I'm running out of paper here. All right, well, next, we'll do a few more. N equals 6. So that would be 12 minus 3. That's 1 over 9. 12 plus 3, 1 over 15. And n equals 7. And I think by now we'll see what's happening here. So for n equals 7, we have 1 over 14 minus 3 is 1 over 11. And 1 over 14 plus 3 is 1 over 17. And ... Now, what's happening here? Well, what happens is we see that certain things pair up and cancel. So there's a 1/7. That's going to cancel with a 1/7 3 terms down. There's a 1/9 here. That'll cancel with the 1/9 3 terms down. So that's going to be gone. There's a 1/11, and that's going to cancel with the 1/11 3 terms down. And in fact, there's always going to be something 3 terms down. Now you might say, well, why is it 3 terms down? We can actually see why. Let's come back up here for a second. So 1 over 2n minus 3, that's my first term. I'm going to subtract. Now, I want to think this as 1 over 2 times something minus 3. Now the question is, what needs to go here? Well, I'll need a 2. So this is 2n minus 3. So what do I need to put here so that 2 times something minus 3 gives me plus 3? Well, the answer is plus 3, right? 2 times 3 is 6, minus 3 is 3. So notice here, and this is how you can sort of see what's happening. This is shifted 3 pieces, or if you like, 3 spaces. So that's why when I have this 1/7 here, I shift 3 times, and now the second term matches with the first term 3 terms down. Again, the second term, go 3 terms down, matches with the first term, except for the sign, so you get cancellation. So you get all this cancellation. So that says, for example, that all these last pieces are going to cancel with something 3 terms down. Now, you have to be careful with telescoping. The other thing to ask is, what happens to the last term? So, do these terms go to 0? If the answer is yes, then we just need to say, well, what's left at the start? If the answer is no, we've got to be a little bit more careful. So what happens to 1 over 2n minus 3 as n gets big? Does it go to 0 or not? It does. Right, it does. So what happens is it telescopes, and the end of the series goes to 0 in the partial sums, so we are left with just the only things that are left are from our first 3 pieces, because they didn't cancel with anything. So 1 plus 1 over 3 plus 1 over 5. Now, get a common denominator of 15. 15 15ths plus 5 15ths plus 3 15ths gives us a grand total of 23 15ths. And that is our answer. And there we go. All right, good. Nice, nice. Okay. Number 4. Find the sum n equals 1 to infinity of something that looks terrible. Yeah, I agree. That does look terrible. But again, we have the word find, which means we're either going to be talking geometric or telescoping. Which one? It's got to be telescoping. Because if we were going to be geometric, we'd have to have something to the nth power. We don't have that here. So, all right. So we need to make it look telescoping. So we need to rewrite it as something minus something. Well, how do we get there? That's not so clear. Well, suppose this was our expression to start with. And we can suppose that because this is our expression to start with. So that's not such a hard thing to suppose. All right, what can we do to simplify it, to make it look better? Because oftentimes that's what we need to do. We need to say, all right, well, this isn't the right kind of form, but maybe, just maybe, if we work with it, it will become better. So, probably what we can say is, well, look, I really don't want to have something added or subtracted downstairs. I really want the adding or subtracting to happen upstairs. And also, I don't like these square roots downstairs. So this is suggestive that we should use the conjugate. So the conjugate can help us. It can help us get rid of square roots. It can also help us by introducing something being subtracted upstairs. That's where we want the subtraction to happen. So we're going to still have our 2 terms, n plus 3 square root of n minus n square root of n plus 3. So this is the sign that we changed, the one in the middle. Well, whatever we do to the bottom, we got to do it to the top. So n plus 3 square root of n minus n times square root of n plus 3. Okay, well, what does that become? So we still have our summation. We haven't done anything with the sum yet. All we're doing is working on rewriting the terms. So upstairs we have 3 times n plus 3 square root of n. I'll put a really big parenthesis here. Minus n square root of n plus 3. We'll deal with that when we deal with that. Let's work on the downstairs. So first thing is we'll square that. So that would give us n plus 3 squared times n. Because n plus 3 squared, then that'll become n. Minus, now we square this. Because remember, if it's a plus b, a minus b, a squared minus b squared. So minus n squared times n plus 3. Well, at least the downstairs, there's no square roots, so let's simplify that. So let's not expand it out. Let's just sort of factor out what's in common. because they both have n plus 3s, they both have n's. So that's summation, n equals 1 to infinity, 3 times n plus 3 times square root of n minus n square root of n plus 3. And downstairs you have an n plus 3 times n, because that's common, and then you're left with n plus 3 from the first term and minus n from the second term. Now, let's stare at this for not too long. I think we can see some things that are happening. Notice the n's cancel. So this is 3. But wait a second, there's a 3 there. So the 3's cancel. So that's great. Now, what do we want? Well, remember, our goal is to get a sum of something minus something. So we want to break this up as 2 terms. So let's break it up using this minus sign. So this is a summation, n equals 1 to infinity of n plus 3 times square root of n divided by n plus 3 times n minus n square root of n plus 3 divided by n plus 3 times n. Alright, so we broke up over the numerator. Now, can we simplify anything? Well, yeah, we can. See, like in the first term, the n plus 3's cancel. In the second term, the n's cancel. But actually, we can do a little bit more. See, notice how you have a square root of n over n? What is that? Well, that is 1 over square root of n. How about square root of n plus 3 over n plus 3? Well, that is 1 over the square root of n plus 3. And now we say, aha, that does have the telescoping form. See, because it's a subtraction, but also there's a shift. So this is n plus 3, which means that when we start writing terms down, so we'll get 1 over square root of 1 minus 1 over square root of 4. And the next term will be 1 over square root of 2 minus 1 over square root of 5. And the next term will be 1 over square root of 3 minus 1 over square root of 6. And then the next term will be 1 over square root of 4 minus 1 over square root of 7. Now, of course, we can keep going, but not for too long because I'm about out of paper here. But what's the point? Well, the point is this plus 3 says that if I look at this second term and I go 3 terms down, I'll find something that cancels it. So those cancel. Go to the second term, 3 doors down, they cancel. And in fact, that's always going to happen. 3 down. Now, one thing to be careful about is what's happening to these terms. Do they go to 0 or not? And if they go to 0, then we can ignore the end, because it says the end is going to get small and we don't need to worry. If it doesn't go to 0, we've got to be careful. But these do go to 0, which means that everything else will cancel out. All right, so what's left? Well, what didn't cancel is the stuff at the start. And you have 3 terms. So you get 1 plus 1 over root 2 plus 1 over root 3. Now you can do something fancy, and you can say, suppose I wanted to obfuscate. Now, for example, I can make this root 6 over root 6. Here, if I want to make the root 2 to root 6, I can make this root 6 and root 3, right? Because 3 over 6 would give us a 2 downstairs. And then a root here, it'd be a root, what would it be? Root 2 over root 6. So I can make this square root of 6 plus square root of 3 plus square root of 2, all divided by square root of 6. And now I've completely obfuscated what I did. But, of course, that's if I want to obfuscate. This is also a really beautiful answer as well. All right, good. That's fun. All right. Number 5. All right. Find Good. More finding problems. It's great to do these because we're going to get into some quizzes in the future where we don't even get to find anything. We're just like, well, what can we say? We're kind of heading towards yes or no questions. So let's enjoy this time while we can. So find 3 to the n plus 4 to the n divided by 5 to the n equals 0 to infinity. Well, we're thinking geometric or telescoping. Which one should we think of here? We should definitely think geometric because we think of things to the nth power. But we got to make it look geometric. Right now it doesn't feel very geometric. So our goal of geometric should be we want something that looks like sum n equals, say, 0. It doesn't have to be 0, it can be anywhere. A times r to the n. So right now we don't want the plus sign and we want just a single something to the n. But that's not so hard to overcome. So for instance, we can think of this as n equals 0 to infinity of breaking up over addition, which that's really nice. It's a nice property that says we can break up over addition. We can certainly do that. Sum n equals 0 to infinity, 3 to the n over 5 to the n plus 4 to the n over 5 to the n. Well, that's the sum, n equals 0 to infinity. 3 to the n over 5 to the n, I can combine those as 3/5 to the n. And in a similar way, I can write this as 4/5 to the n. So that's really good. The only thing is, I don't want that plus there. Well, question. Suppose I have a sum of two things added together. Does this equal the sum n equals 0 to infinity of 3/5 to the n plus the sum n equals 0 to infinity of 4/5 to the n? And the answer is not trivial. We shouldn't say like, oh, of course, it's obvious, it must be true. Because a lot of things which are obvious aren't true. And I guess the converse is a lot of things which aren't true seem obvious. But are we okay? And the answer is yes, we're okay if both the pieces converge. So as long as the individual pieces converge, then we're fine. That's one of the basic rules of limits. It says if I have a limit of two things being added together, I can take the limits individually as long as each one works. So, well, let's see. Is that true? Well, now we are definitely into our geometric. So we'll use our rule for summing geometric series. So in the first case, the sum from 0 to infinity of 3/5 to the n, what's the first term in the series? Well, that's n equals 0. 3/5 to the 0 is 1. Over 1 minus, what do you multiply at every stage? And the answer is 3/5. For the second term, what's the first term in the series? 4/5 to the 0, that's 1. Divided by 1 minus, what do you multiply every time, which is 4/5. All right, so we're good because we can find these sums. Now, 1 minus 3/5 is known as 2/5. 1 minus 4/5 is 1/5. Flip the denominators up. So that's 5/2 plus 5/1. Well, usually we just say 5. And, well, you can really multiply this by 2 over 2 and get 10/2, which gives us a grand total of 15/2, or if you want to, 7.5. So yeah, there we go. There's the answer. That's not so bad. That's not so bad at all. All right, good. Now, next one. Number 6. Suppose that an and n equals 0 to infinity is this set of numbers. So you get 1 over 1, 3 over 1, 3 over 4, 9 over 4, 9 over 16, 27 over 16, 27 over 64, 81 over 64, where you start with 1, that's true, and then you either multiply by 3 or multiply by a fourth, but you alternate. See, so like here we multiply by 3, then by a fourth, then by 3, then by a fourth, then by 3, then by a fourth, so forth, so on. Find the sum n equals 0 to infinity a sub n. Now, we see find, so okay. So it's either geometric or telescoping. Which one? Well, it's not so clear, but I would say it behaves like geometric. Now, what's the clue? Well, notice there's a key word here, multiplying. Now, the way that geometric series work is that at every stage you multiply by a certain value. Now, why is this not just an obviously like, aha, this is geometric? Well, because what's happening is we're not always multiplying by the same amount. Sometimes we multiply by 3. Sometimes we multiply by a fourth. And so it's not like this is geometric and life is good. So how are we going to think of this? Well, let's see. Let's write what we have. So we have 1 over 1, 3 over 1, 3 over 4, 9 over 4, 9 over 16, 27 over 16, 27 over 64, 81 over 64, and let's see, is that enough? We could do another one. Do you know what the next one would be? Well, let's see, what would it be? All right, so the next one, we multiply the denominator by 4, so that's probably why I stopped there. That would be 81 over 256, then 243 over 256. These are some not huge numbers, but not small numbers, and so forth. Now, we're trying to think for geometric. So here's sort of one thing to think about, which is, look, I alternate, multiply by 3, multiply by a fourth. So, suppose I take not one step, suppose I were to take 2 steps. What would happen? Well, I would have multiplied by 3 and by a fourth, so I'm 3/4. Well, how about here? Well, again, multiply by 3 and multiply by a fourth, so that's again multiplied by 3/4. And here? Well, again, because we do both operations, 3 and 4, so 3/4, and so forth and so on. Well, what if we did the similar thing, but now we started 1 over? So, how about here? Well, multiplied by a fourth, multiplied by 3, well, it doesn't matter what order you multiply, it's still the same effect. You multiplied by 3/4. So how about skip 2? Again, multiplied by a fourth and multiplied by 3, 3/4. And again, and again. So what's happening here is that it's behaving like a geometric series, but really it's like you have 2 geometric series interlacing. What we want to do is separate them. And so we can say, aha, what happens here? What happens here? So we can say, all right, so when we're adding these together, what we can think of doing is we'll alternate every other term. So we'll have 1 plus 3/4 plus 9/16 plus 27 over 64 plus ... And then we'll add to that, well, 3 over 1 plus 9 over 4 plus 27 over 16 plus 81 over 64 plus ... Now, each one of these is a geometric series. What happens to the first one? Well, does it converge? You check, what are you multiplying by at every stage? You're multiplying by 3/4. And so, since what you're multiplying is less than 1 in size, it will converge. The first term is 1, so you get 1 divided by 1 minus what you multiplied by, which is 3/4. Now here, does this converge? Well, yes, because we're multiplying by 3/4. That's something smaller than 1. What's the first term? Well, the first term is 3. So this will be 3 over 1 minus, and again, we're multiplying by 3/4 at every stage. Okay. Well, that's really 1 over 1/4 plus 3 over 1/4. But of course, you can take the 1/4 and flip it. So that would be 4 plus 3 times 4, which is 12, giving us 16. And therefore, the grand total is 16. Now this sort of comes into an idea or philosophy which says, let's learn to manipulate things. And manipulating sums is a really useful tool. It says, let's take things that we know and put them into expressions that we're comfortable working with. In this case, it says, let's make things look like geometric because we're comfortable making things look like geometric. And how do we get there? The ability to work with and manipulate these types of expressions are going to become really important, especially towards the very end when we get into some of our last topics. That all comes down to figuring out how do you work with sums. All right, number 7. Suppose x is something and it's less than 1 in size. Find the summation n equals 0 to infinity of negative 1 to the n x to the 2n. All right, so x is, we can think of it as just some fixed number. And all right, so it's some fixed number. Now, again, we see the word find, and whenever we see the word find, that means that we got to be thinking either geometric or telescoping at this point. Well, which one is it? Well, we see lots of n's in the exponents. So when you see lots of n's in the exponents, you should probably think geometric. All right, so let's try to see if we can make it look even more geometric-y. So that would be the sum, n equals 0 to infinity. And one thing we can do is we'd like to have just one big thing raised to the nth power. Well, that's not so bad. There's a negative sign, because that'll take care of that negative 1 to the n. How about this x to the 2n? If I want to write this as something to the nth power, what does that become? It becomes x squared. Well, why? Well, note that x to the 2n is the same as x to the 2 to the n. On a side note, it's also equal to x to the n to the 2, but we want to have that x to the 2 to the n. That's something that's useful, whereas that's just a pleasant distraction. All right, now, does this converge? Well, I have something to the n. And now I ask the question, well, what can I say about the absolute value of negative x squared? Now, it's true that this is the same as just the absolute value of x squared, and I know that the absolute value of x is less than 1, so if I square that, that's still less than 1. So, this is a converging geometric series, right? Because the only thing I need to be able to say in order for something to converge is, if it's geometric, is that whatever I'm multiplying by has to be smaller than 1. So, this is equal to, what's the first term? N equals 0. Well, something to the 0 is going to be 1. Divide that by 1 minus, what do you multiply at every stage? In other words, what's inside of this something to the n? Well, the answer is it's minus x squared. So, that becomes 1 divided by 1 plus x squared. That's it. We're done. Ah, that was too easy. However, knowing the people who write problems, 1 over 1 plus x squared, I suspect we're going to see this again. Maybe a couple of times even. All right. So, number 8. Determine whether the sum n times sine 1 over n converges. All right. So notice it's a different word. So what's not here? What's not here is the word find, right? That's not here. So when it's not the word find, we're actually just asking a simple kind of yes-no question. Does it converge? Does it not converge? Which side are we on? Now, for these types of questions, there's a handful of tests. And we're going to get more and more tests as we go on. But at this point, we have 2 tests. One of them is the nth term test. And this is also called the basic divergence test. And the other one is the integral test. Now, the integral test says, suppose this were a function and you integrated it. well, what would happen? Well, that would be the function x sine 1 over x. I don't want to integrate that. So let's think about the nth term test, because that looks like there's a chance. So the idea here is this is our a sub n. And let's look at the limit as we get big. N goes to infinity of a sub n. Well, that's the limit as n goes to infinity of n sine 1 over n. Now, what's happening? Well, what's happening is that this is getting big because n is getting big, right? 1 over n is getting small, so that's getting small. And so sine of 0 is 0. So it's going to infinity times 0, which is more work, right? Because who knows what infinity times 0 is? It's an ambiguous answer. Now you're probably thinking, he's going to do l'hôpital. Well, maybe. But wait a second. Before we do that, let's make a little observation. This is the limit as n goes to infinity. If we were going to do l'hôpital, it would be sine 1 over n. Divide that by, the n would go downstairs, 1 over n. Now, what do you see here? The 1 over n's are the same thing. Now here's a fun fact. Sine of something, which I'll write as blah, over blah, goes to 1 as blah goes to 0. So we're of the right form, right? Sine of the inside here matches with what's downstairs. Sine of something over something. This is going to go to 1 as long as the inside goes to 0. Well, what happens to 1 over n as n goes to infinity? It goes to 0. So, what does that mean? Well, it means that this is 1. So, what does that say? Well, it says if you add these numbers up, so you're adding up the sum, n equals 5 to infinity of n sine 1 over n, well, you get some numbers at the start, 5 times sine 1/5, 6 sine 1/6, and so forth and so on. But if you get really big, so this is going to be something, and it's going to be, well, 0.99999. It turns out slightly below 1, plus, again, 0.9999, again, and so forth and so on. So what's happening is at the end, you're adding up these numbers, which are all very, very close to 1. So if you add up a lot of numbers which are not small, you're going to get something which is big. So the conclusion is, since this limit is 1, which in particular is not 0, and by the nth term test, the sum diverges. Or, well, we could say the sum does not converge. Now we could, depending upon how we were feeling, we could say, on a side note, with the nth term test, because the nth term converges to some positive number, well, it says really on the end we're going to add up a whole bunch of positive numbers. You could say it does that behavior. But generally speaking, we would say the sum does not converge. All right. Good. Good. Now, next one. Number 9. Determine whether the sum n equals 0 to infinity of 1 over n squared plus 1 converges. All right. Well, we don't have very many tests. So again, what do we have? Well, we have the nth term test and we have the integral test. Now the nth term test is oftentimes really easy to eyeball. As n gets big, what happens to this expression? Well, it gets small, goes to 0. So, what does the nth term test tell us? It tells us nothing, right? Because when the terms go to 0, we don't know. So the nth term test is inconclusive. All right, well, that's just our way of saying we can't use it. And since we only have 2 tests, by process of elimination, we better do the other test. So we'll do the integral test. So we think of this as a function of x. So integrate 0 to infinity, 1 over x squared plus 1 dx. Well, what is the integral of 1 over x squared plus 1? Aha, I said we'd see it again, right? Well, we know what that integral is. That's arctangent. So arctangent of x from 0 to infinity. Now, we plug in infinity. Of course, you don't plug in infinity because you can't. It's a huge number. But what you do is you say, well, what's happening to arctangent as you head to infinity? And the answer is arctangent approaches a horizontal asymptote. And therefore, arctangent of x heads to that asymptote of pi over 2. And then subtract arctangent of 0, which is 0. Now, really, we don't care about this bound. That's not important. The real question is, what happens at infinity? Why is that important? Well, because remember, the question is, what's going on with the tail? It's the tail that tells you whether things converge or diverge. Now, this value is not important. What is important is that this value is finite. So this is small. So what does that say? Well, since the integral converges, then the conclusion is the sum also converges. Because the integral test really says whatever one does, the other does. If the sum converges, the integral converges. If the integral converges, the sum converges. And so they're tied together. And so that's the answer. It converges. Yes, yes, good. All right. Well, now we'll tweak it ever so slightly for number 10, our last question for this quiz. Determine whether the sum from 1 to infinity of 2n over n squared plus 1 converges. Well, again, we should just sort of eyeball and check what happens with the nth term test. Well, if you look at the terms, you'll have a big number over a really big number, right? Essentially, it's like n over n squared. It's about 1 over n. Well, that's going to get small. So, inconclusive, because the terms go to 0, so it might converge, it might not converge. We don't have enough information at this point in time. So, well, now we turn to our other test. So let's look at our other test. 1 to infinity of 2x over x squared plus 1. Now, technically, you got to be a little bit careful. Is the function 2x over x squared plus 1 decreasing? And the answer is not initially. At first it goes up, but then it starts going down. And so the important thing is that it goes down eventually. We don't really care about the behavior at the start. Behavior at the start is not important. It's this behavior over here at the end. That's the behavior that matters. So, okay. So we're positive, we're decreasing, we can apply the test. So, can we integrate 2x over x squared plus 1? It's not arctangent, but it's not so far off. What do? Well, if you set u equal x squared plus 1, what would du be? It'd be 2x dx. So, it's like the integral of du over u, which becomes the natural log of u. So the integral of 2x over x squared plus 1 is the natural log of x squared plus 1. Evaluate from 1 to infinity. Again, plug in infinity, which we say, well, what happens as we go to infinity? Well, the inside of the natural log gets bigger and bigger. So what's happening is that the inside is getting big. Natural log of a big number is big. Yeah, it's big-ish. Natural log really doesn't want to go to infinity. It desperately wants to stay small. But if you're patient and you go out far enough, it gets arbitrarily large. And therefore, what happens is when you plug in infinity, it goes to infinity. Now, do we care about what happens at 1? Well, no. It doesn't matter. Because, it's going to be some finite number. And look, however big this small finite number is, and this is a small number, it's hard to recover from infinity. So this is infinity. So what does that mean? So the integral diverges. That's what we figured out. because we can use our tools from doing improper integrals. Now, once we know the integral diverges, the integral test says that these two things come together. And so, our conclusion is that the sum also diverges. Now, of course, diverges is just a fancy way of saying does not converge. And there you go. So yeah, this shows you, if you compare the previous two problems, numbers 9 and 10, you'll see that the nth term test really is not very conclusive, right? Because here, on number 9, we saw, hey, the terms went to 0 and the sum converged. Here in number 10, the terms go to 0, the sum diverges. And so you got to be really careful. A lot of people think the nth term test is very powerful. It's actually very weak. You know, not surprising because it's a very simple test. Usually the simpler the test, the weaker it is. But anyways, that's the problems for this quiz. And we still have a couple more quizzes to go. And so, well, lots of fun problems still to come. All right. So, my friends, take care of your health. We'll see you next time. Bye.